All right, we're running a little bit early, but we'll continue and leave a little bit more time for questions at the end. Our next talk is by Irene Cogliati, the Exploration-Exploitation Dilemma as Tool for Studying Addiction.
Okay. So I will thanks the organizer to organize this lovely conference. I'm going to give you information concerning the first part of the title, and I'm going to present the dilemma from a different perspective that have been shown today, and then I'm going to straight to the second part. So I've been recently traveling to Peru with one of my friends who already been there several times, and during our travel, she was facing the following dilemma: whether to come back to Machu Picchu, that she really enjoyed, or whether to explore additional spots that she'd never been before. So during our travel, she was facing the exploration-exploitation dilemma. In particular, she needed to choose between exploratory options associated with stronger reward history, or to choose among alternative options with uncertain value. On the top of that, if she decided to explore, she needed also to understand how to explore. So she could pick up one of the two options at random, or she could direct her explorations toward one of the two options, for example, Titicaca Lake. Because she's never been in both spots, but she never seen any pictures, so she never heard anybody talking about the Titicaca Lake, whereas she has seen pictures concerning Ocachina Desert. So if she wanted to learn and to have an optimal understanding of Peru, she needed to direct her exploration toward the most informative options. And it has been shown that humans can solve the exploration-exploitation dilemma using both directed and random exploration. It has been hypothesized that the dilemma can be used as a powerful tool for studying psychiatry disorder. And this is true for a few reasons. The first reason is that the dilemma is common across species, and which allows preclinical and translational research. But also, there is accumulation of evidence concerning neurobiological and neural mechanisms underlying the dilemma. And lastly, there is the computational mechanism underlying the dilemma can be used as a quantitative assessment for the neurobehavioral mechanism underlying it. Thus, the dilemma can tap into a deep neurobehavioral decision-making schema pertinent to the health and fitness of an individual, suggesting that it can be used where this schema are altered, such as in psychiatry disorder. So what I'm going to argue today is that the exploration-exploitation dilemma can be a useful tool for studying addiction. Addiction is defined as a loss of control over drug and not drug behaviors, despite negative consequences. And this loss of control arises from an imbalance between responses toward reward stimuli and inhibitory control over those responses. And because the addictive processing are presented in that way, the dilemma can be useful in order to understand the alterations behind addiction. During my research, I focused on pathological gambling. In particular, pathological gambling is a behavioral addiction that does not involve the intake of exogenous substance. Although in this population presents both the same symptoms of addiction as well as similar neurobehavioral alterations. Because there are no intake of exogenous substance, pathological gambling can be considered as a pure model of addictions where you can actually investigate addictive processing without having confounding effect of chemical substance. So in this study, we decided to investigate decision-making alterations in probable gamblers under the exploration-exploitation framework in order to gain insight into addictive processing. If you think about studying the exploration-exploitation dilemma in a lab, you may start picturing the famous multi-arm bandit task. For who doesn't know, this is a reinforcement learning problem where on each trial, an agent or a participant needs to choose among alternative options. In this case, the options are 3 different decks of cards. And each time they select an option, they can get a reward. And in this case, the reward is between 1 and 100 points. And the goal of the decision maker is actually to make sequential decisions in order to maximize the total amount of points earned at the end of the task. So it needs to win as much as possible. Because the multi-arm bandit task implies sequential decisions, there is a reward information confound that arises in trial by trials. In particular, when the decision maker is going to select one option, it can get both the reward associated with that option, as well as the information concerning the quality of that option. Because of this information reward confound, it's really hard to discern at the behavioral level a random and directed exploration. This is the reason why Wilson and colleagues came up with this new design, where they actually added a 4-choice task at the beginning of the standard bandit task. And in the 4-choice task, they actually, by adding this 4-choice task, they actually were removing reward and information confound. In particular, in the 4-choice task, information was manipulated. In the unequal information condition, for example, the 3 different decks can be, the participants are forced to choose the 3 different decks at different rate. For example, 2 times the blue deck, 4 times the red deck, and never selecting the green deck. On the contrary, in the equal information condition, the 3 decks were sampling on the same rate. This actually removed the reward information confound in the first 3 choice trials of each game. And this is because if they are going to select the green deck in the equal information condition, this deck has never been associated with reward, but is actually the most informative deck. On the contrary, in the equal information condition, there are no differences in terms of information, and choices can be labeled in terms of reward. So if they are choosing the option that is not the best option, they actually random explore in the environment. If you think about the learning problem faced by participants during this task, you may think that they're actually learning reward on a trial basis. And the way they're actually learning reward is by making predictions concerning the next outcome, and then updating this prediction through a prediction error once the outcome is delivered. And the way actually the prediction error is integrated into next predictions is dependent on the learning rate of each participant. However, they may also start to accumulate information over time. And the way information is modeled here is really abstract, and it's tried to capture only the sampling rate of each option. So you have to imagine that each participant has a kind of vector, and each time they select an option, they had 1, and each time they don't select an option, they had 0, and then they sum all up, and it's gonna give them the information value. And this information value is then raised at the power of gamma to add some nonlinearities to this process. Then information and reward values are integrated in choice values, and the way this is integrated is depend on this parameter here, omega. And also this integration tries to capture a particular phenomenon, which is actually the more an option is selected, the less participants is willing to explore that option. So eventually the value of the option is gonna go down, and it's gonna favor the exploration of other alternatives. And this model actually integrates as of max selections in order to make its choices. And it's going to assign higher probability options with higher values, but sometimes it's going to also select options with lower values. This is going to depend on the beta parameter. If you make this model play with the task that I just showed you before, and you analyze the first 3 choice made by the model in the unequal information condition, you can see that actually the model is selecting often the option that has never seen before, which was the green options of my example. And this is a behavior that actually we observe in participants, in human participants. And however, if you remove this part from the model is no longer able to mimic participants' behavior, which suggests that both reward information needs to be integrated somehow in order to solve exploration-exploitation problems using random and direct exploratory strategies. So in this study, we tested 22 control and 40 gamblers. They were matched at the level of mean in terms of age, IQ, memory capacity, attention control, and so on and so forth. However, they were different in terms of gambling severity. In particular, control did not show any problem gambling. Although they might experience gambling in the past years, but not in the year before the study. We also selected gamblers that were not going under treatment. And in order to remove the chemical confounding effect, we tested participants that were not assuming alcohol dependence. They were not actually showing alcohol dependence and substance dependence. Although we had few participants that were showing meat and weak smoking dependence, because removing them from the analysis did not change the statistical results. So both groups play with the modification, the modified version of the bandit task, and they play this 4-choice task and 3-choice task for 162 games. And then we analyzed their choices in the first 3-choice trials. And we find that in the unequal information condition, probable gamblers were reducing direct exploration, and they were increasing exploitation compared to controls. On the contrary, in the equal information condition, we did not find any differences in terms of exploitation and random exploration. This suggests that alteration in the manner in which the dilemma is solved are specific to goal-directed exploration and to scenarios where the environmental contingencies change. Because in the unequal information condition, the third option is made available after 6 consecutive trials. So actually, you introduce changes in the environment. However, which are the hidden mechanisms underlying the exploration-exploitation unbalance that we observe in the unequal information condition? In order to answer this question, we fitted the reinforcement learning model that I presented to you at the beginning. And we estimated the value of the 3 parameters. And then we compare between groups. What we observe is that the information integration were reduced in problem gamblers compared to control, which actually changed the sign of this minus here, so it became a plus. And which says that the more an option is selected, the more the values are going to increase, and the more you're going to stay with the same options. However, we also observe an effect in the information decay. Especially, we observe an increase in information decay in problem gamblers compared to controls, which suggests that additional observations are also penalized in this group. This information integration has been associated by our group to cognitive control. In particular, reducing cognitive control resources affected the manner in which humans integrate information into values. And additionally, this information value here, which is just the amount of information obtained from each option, negatively correlated with dorsal ACC and anterior insula, which are the main component of the cognitive control system. This actually suggests that problem gambler might decrease directed expression as a consequence of an impairment in information processing. And also, the inhibitory control processes impaired in substance and behavioral addictions might relate to this information control signal. We also investigated reward learning during this task, and we observed a reduced learning rate in problem gamblers compared to controls. So problem gamblers were less able to integrate new reward information from the environment. And this learning impairment can actually explain one of the phenomena observed in this population, which is the loss chasing phenomenon, which actually is the more they're actually losing money, the more they are gambling, which actually suggests that even though there are changes in the environment, they are not really able to update these changes and to act accordingly. However, this learning impairment may also explain the fact that they are not able to stop gambling despite negative consequences. And this particular symptoms is exactly the same symptom observed in substance abuse. And so these results can help us reinterpret this phenomenon as a learning impairment. Finally, we also try to see whether this behavioral alteration that we observed were actually driven by alteration in decision noise. Although however, we did not observe any differences, significant differences between problem gamblers and controls. So the take-home message of today is that exploration-exploitation framework is a powerful tool for studying addiction, and the problem gamblers can be considered as a pure model for studying addictive processing, in the case, of course, there are no comorbidities with substance and alcohol dependence. Decision-making impairments in problem gamblers are expressed as information and reward learning alteration. And this information and reward learning alteration can explain the main symptoms of addiction. Now, just to conclude, if you are worried whether my friend that I showed you in the first slide is actually showing symptoms of addiction, she actually did not. She left me alone in Machu Picchu. And she decided to directly explore the environment, and she came with me to Titicaca Lake. Now, exploration is really important, but too much exploration is not really important, and this can really arise from depressive conditions. So perfect balance between exploration and exploitation is necessary. So now I'm going to thank my collaborator, Angela Yu, Axel, Cleeremans, and Xavier Noel, my FNRS fundings and ERC funding from Axel, and I'm going to thank you for your attention.
Hi. Very interesting talk. So I have a question about your model. So you showed this phenomena where in the unseen version, the participant would choose the unseen option very often, right? Can this be explained also by if I just have a higher prior, that I have a prior that the unseen one has some reward that is higher than the average reward that I got from other options? In that case, the participant or the agent would naturally choose the unseen option, right? And then you can model the difference between the control group and the pathological gamblers using different prior.
Yes, I think if you have higher priors, then you're going to select the unseen option. However, in the model, we actually run a reinforcement learning model over thousands of observations in order to understand which were the priors used by the model. So actually, the prior are learned in this context. And in previous study, we actually compared this way of learning by general priors by actually updating games by games. And we showed that actually this way was better. But yes, I think going in that direction, which are actually priors, might be actually an interesting investigation. Yeah.
Thank you.
Hi. So what I was understanding, so in the pathological gamblers, you were showing negative values of omega. Was that correct? And does that mean that the participants are actually showing the gamblers are actually showing a bias towards sampling the option which is they've seen more information on? Or was I misunderstanding that?
No, because actually there is a minus there. So actually there is no a plus. So if actually in the normal situation, if there is a minus, it means that actually if you increase the omega, that value is going to increase and they're going to reduce the value of the chosen option. Okay? In these scenarios, actually, it's become a plus. So the more you select an options, the more it's going to add to reward value, and the value of the chosen option is going to be even higher.
Yeah. So the option which has just been chosen,
it's going to be chosen even more. Yeah,
okay,
exactly.
Okay.
There is no expression of alternative options. Yeah.
Thanks.
Yeah.
Hello, very interesting results. I also have a question similar to this, or somewhat related to this. Is that it seems that this model kind of learns the optimal solution if you assume that the samples are IID. And have you considered whether the participants actually assume that there is some kind of temporal dependence between the samples? For instance, if you pull cards from a deck, then if you haven't won for a while, then your chance of winning increases, actually.
The temporal dynamics is captured from the gamma parameter, but yes, there is no like a decay in the reward values. So this is just concerning the information. So there is a decay concerning information, but there is not a decay concerning reward values. Did I answer your question? No. Okay.
So this may clarify a little bit because this is related to the other two. So you cited some of Marathaticot's stuff, and what we find in smokers is that they do a lot of subsampling. So the samples are very clustered around 5 or 6 samples of a bandit. So it doesn't necessarily look like independent samples. It looks like they're choosing things 5 or 6 times to get a quick estimate, and then they move on. That would equate to, I think, a negative omega in what you're doing, but it does break this assumption that trials are independent. And so it'd be interesting to look at, say, the run lengths for choices to see if they fit the assumptions of the model, which I think should be exponentially decaying. So I guess the right question is, do you tend to see people doing this sort of clustered sampling as if they're sort of estimating law of small numbers or something?
No, actually, I have to think about this question, and no, I didn't say this. But I would like to talk about more